Hello everyone, this presentation is part of the MedEWSa project and introduces the concept of parametric triggering and loss catalog creation within a catastrophe modeling framework developed for the MedEWSa CAT model. The content is based on presentations delivered at the MedEWSa General Assemblies in September 2025 and February 2026. We begin by briefly placing parametric triggering and loss catalogs in the context of parametric insurance and catastrophe bonds, before focusing on their application to wildfires in the Ethiopia use case. The aim of the MedEWSa CAT model is to create the underlying data for the financial structure of a catastrophe bond. Parametric insurance, including catastrophe bonds, is a financial mechanism used to transfer risk from natural hazards. While originally developed in the 1990s and widely used for hazards such as hurricanes and earthquakes, we are now exploring its application to wildfires. A key requirement for parametric insurance is the definition of a parametric trigger and the generation of a loss catalog. This trigger must be strongly correlated with losses reported by an independent data source and associated with each event in the loss catalog. A loss catalog is a collection of many parallel events, each associated with an estimated economic loss and the corresponding hazard parameter. In our case, losses are modeled rather than based on reported historical damage, as observed loss data are insufficient for robust statistical analysis. The losses are calculated by multiplying the exposure with the damage function evaluated at the intensity of your location. The damage function describes what fraction of the exposed value is lost under a given hazard intensity. This formulation is common across many hazard types and forms the basis for constructing loss catalogs. For wildfires, we begin with historical burned area datasets retrieved from global sources such as the Global Wildfire Information System. As the data are global, the method can be replicated to any other location as well. This system provides more than 20 years of spatially explicit fire data with global coverage. Each recorded event includes its spatial extent and timing. This allows us to compile a large number of fire events, particularly in Ethiopia, where thousands of fires may be recorded each year. Initial analysis of these datasets helps us understand fire frequency, spatial patterns, and the statistical distribution of burned areas. We can also have a first indication about the suggested parametric trigger. In this case, for example, a good first guess would be the size of the fire, which nevertheless might not be the finally selected trigger when the data are analyzed in depth. As a first step, we can proceed with exploratory data analysis and visualize the frequency of wildfires in our domain, either in a fine resolution of 1 kilometer, as the left figure, or in coarser resolution of 100 kilometers for getting country-wise information, as in the right figure. From this figure, we can see, for example, that most fires occur in the western part of Ethiopia. The statistics of the recorded events show a wide range of burned areas, with the smallest one being 21 hectares and the largest one over 18 million hectares. For parametric insurance applications, we are particularly interested in extreme events, so we can have a better look at the extreme events after fitting a distribution and checking its tail. In our analysis, the log normal function had the best fit from the selected functions. Using extreme value analysis, we estimate the size of fires associated with specific return periods, such as a 1 in 20-year event. This analysis is performed using annual maxima and standard statistical methods implemented in Python. To do so, the best function that fits the underlying annual maxima data is selected. These return levels could be used as candidate insurance triggers, provided they are sufficiently correlated with economic losses. One thing that should be kept in mind is that with a 20-year dataset, we can't really calculate return periods over 20 years. Although such values are plotted in the figure, which goes up to 100 years, the uncertainty is very high, and values corresponding to over 20 years return periods should be treated with caution. From the conducted analysis and the chosen return period of 20 years, we retrieve a return level of 3.7 million hectares burned area as a potential trigger for parametric insurance. This is the first indicator we can further analyze as a parametric trigger for insurance. Loss calculation requires not only hazard data, but also appropriate vulnerability assumptions. Remember that the loss is the product of exposure and damage function evaluated at a specific hazard intensity. Our partners in Ethiopia indicated that the assets of interest are the crops and the villages. For crops, wildfires are highly destructive. Based on findings in the literature, we assume binary vulnerability. This means that wherever a fire occurs, all crops within the affected area are considered completely destroyed. For villages, we rely on vulnerability functions derived from previous studies rather than developing new ones, as we don't have enough data to do so. In particular, we used information from the CLIMADA framework, a recent work that used observed damage data to calibrate vulnerability functions. The data have global coverage, and the work is open access. The good thing is that there are different damage functions for different resolutions. An important result from the literature is that when exposure data has sufficiently high spatial resolution, vulnerability functions tend to converge towards binary behavior, as it can be seen in the plots on the left column. At high resolution, it is therefore reasonable to assume that if a fire affects a pixel, the exposed value within that pixel is fully lost, leading again to a binary behavior. More complex damage functions mainly become necessary when exposure datasets are coarser. Such aggregated information is useful for stakeholders interested in overall loss that is expected in the society, such as NGOs and governments. Stakeholders with individual assets, as for example list of factories around the globe, would need information tailored to their needs. For villages, exposure is represented using the CLIMADA LitPop dataset, which is of a high resolution, sufficient for proceeding with binary analysis. This dataset combines nighttime light intensity and population density to spatially distribute macroeconomic indicators. The primary economic input is total capital derived from a World Bank Global Exposure Report published in 2014. These values are disaggregated to grid cells of approximately 1 kilometer resolution. Areas with higher population density and brighter nighttime lights are therefore associated with higher economic value. For crops, exposure is derived from Copernicus land cover data at 10-meter resolution, which identifies where croplands are located. In the map on the right, these locations are shown with the pink color. This dataset does not distinguish between different crop types or their individual economic values. To estimate crop value, we apply an average crop value based on figures published by the Food and Agriculture Organization of the United Nations. Refining crop-specific valuation remains an area for future improvement. Now that we have the required information for the hazard, the exposure, and the vulnerability, we can put all the data together and model the expected loss for all the events in the catalog. This graph shows the crop losses for all the recorded wildfire events in Ethiopia throughout the years. There is high variability, with the maximum being almost 26,000 hectares associated with an event in 2004. The minimum value is 60 hectares. These values refer to single events. When aggregating on annual statistics, the mean area of crops being burned due to wildfires is 240,000 hectares, which is a significant amount of damage. In a similar way, we can quantify the impact of wildfires in the urban areas. Here the units are millions US. The variation is smaller, and there are recorded events that correspond to no damages. The maximum damage from a single event is over 11 million US. As for the annual statistics, the wildfires result in losses of almost 185 million US on average, with the most impactful year resulting in 267 million US of losses. We have now introduced the key elements required to construct a loss catalog for wildfires, including hazard data, vulnerability assumptions, and exposure datasets, and we have seen how the combination of these elements lead to the final quantification of the risk with losses in crop and urban areas. These components allow us to estimate expected societal losses in a consistent and transparent way. This is particularly relevant for governments, non-governmental organizations, and early warning and risk financing applications within the Ethiopia use case. Thank you for your attention.